Hello students, we'll continue with the A part of chapter 8, that is some terms related to wave motion. First is amplitude. Now when a wave passes through a medium, the maximum displacement of the particles of the medium on either side of its mean position is called its amplitude, and it is denoted by letter A. Its SI unit is meter. Now this is one of the wave motion, displacement versus time graph. Now this kind of crest and trough will form. So here crest, trough, crest is the part. So this disturbance from the mean position towards extreme position, this is the mean position and this is the extreme, so this is called amplitude. Okay, so in trough also you will get amplitude, and in crest also you will get amplitude. Both amplitude will be equal. Now time period, second term is time period. So this is the time taken by the particle or the medium to complete its one vibration, or the time period of one wave. It is represented by capital T and SI unit is second. So the distance between two consecutive crests is called one wave, and the time taken by the wave to complete its one cycle is called its time period. Frequency, the number of the vibrations made by the particle of the medium in 1 second, is called the frequency of the wave, or you can say in simple words, number of cycles per second, number of waves per second. So frequency is the reciprocal of time period. Its SI unit is second inverse or hertz. Fourth one is wavelength. The distance traveled by the wave in one time period of vibration of particle of the medium, that is called its wavelength. It is denoted by letter lambda, which is Greek letter, and its SI unit is meter. Its value depends on medium in which the wave travels. So the distance between two consecutive compressions or between two consecutive rarefactions is equal to one wavelength in case of longitudinal wave, but in transverse wave the distance between two consecutive crest and two consecutive trough is equal to wavelength. So this is the distance between two consecutive crest. This is called the wavelength. So in this graph it will be very easy for you to understand, because this is the shape is similar, but this is the displacement distance graph and this is the displacement time graph. Now you can see the distance between two consecutive crests is called one wavelength, that is lambda. Wave velocity, the distance traveled by a wave in 1 second is called its wave velocity or wave speed. Now it is the speed with which energy is transferred from one place to the another place by wave motion. It is not the velocity of an individual particle vibrating about its mean position. It is denoted by letter V and its SI unit is meter per second. This is displacement time graph, as I already discussed this, and this is the displacement distance graph to express wavelength. Now relationship between the wavelength, wave velocity and frequency, very important relation. So in this relation, lambda, that is the wavelength, is equal to distance traveled by the wave in one time period or in t second. So wave velocity into time period, and lambda is equal to Vt. This is lambda over here. So this is the relation, Vt is equal to lambda. Now T we can write as 1 by f. You can substitute here, T is equal to 1 by f. So V into 1 by f is equal to lambda, and V is equal to f lambda. By cross multiplying you will get V is equal to f lambda. V is the wave velocity, f is the frequency, and lambda is the wavelength. Very important relation. Now the speed of the sound in different media. As you know, the speed of sound depends upon two factors. That is, the speed of the sound in medium depends upon the elasticity of the medium, and second one is the density of the medium. So with the elasticity it is directly proportional, and with the density it is inversely proportional. So Newton assumed that when sound travels in a gas, temperature of the gas does not change, and it is an isothermal change where temperature means same. So he replaced this E elasticity with the P pressure, and for an air at normal temperature and pressure NTP condition, pressure is equal to 1.01 into 10 to the power 5 Pascal. Density of air was 1.293 kg per meter cube, and velocity, by substituting the values we were getting 279.5 meter per second. but it is quite far from the experimental result of the velocity of sound in air, that is 330 meter per second. Then one more scientist was there, that is Laplace, and he did one correction in the Newton's formula, in this formula, by introducing one constant, that is Laplace constant gamma. And he considered that formation of compression and rarefaction, there is no exchange of heat in the medium, and this is an perfectly adiabatic change. In adiabatic change, there is no transfer of no exchange of heat in the medium. So elasticity, Newton replaced elasticity with P only, but Laplace introduced one gamma as a constant, and this gamma is equal to ratio of Cp over Cv, that is specific heat at constant pressure to the specific heat at constant volume. For air, the value of gamma is 1.4. After introducing this and substituting the value of P and density of air, we got the result quite close to the experimental result, that is 330.7 meter per second. So which agrees with the experimental value. So speed of the sound in different media, the speed of the sound is more in solid, less in liquid, and least in gases. In air it is 330 meter per second, and in water it is 1450, and in steel it is 5100 meter per second. So there is a huge difference. In solid, maximum speed of the sound we can hear. Here is the example that I have considered. In steel it is 5100 meter per second, and in air it is 330 meter per second, and in water it is 1400 meter, 50 meter per second in water at 0 degrees Celsius. Different examples we have, examples showing that speed of the sound in steel is more than that in air. If the sound is produced at one end of a very long steel bar, now two sounds are heard because two mediums are present over there, one is air and one is this solid steel bar. So one which reaches first is propagated through the steel, and the other which is heard later, that is through air, because speed of sound in steel is more than the speed of sound in air. Second one, a person living near the railway track often presses air against the steel rail to guess whether a train is coming or not, although it is risky. But just to differentiate, like in solid the speed of the sound is high as comparison to the speed of sound in air. So the reason is that vibration produced by the moving wheels of the train travel much faster through the steel rail than through air. So sound is heard through track much before it is heard through air. Thus the person, by hearing sound through the steel rail, gets an indication of coming of train well before its sound is heard. Factors affecting the speed of the sound in gas. So first factor is the speed of the sound in a gas is affected by the change in density, temperature, humidity, and direction of wind. First of all, effect of density. From the relation we know V is equal to gamma P upon rho. It is clear that gamma P is related to the numerator part. We will consider the denominator, density. Speed of the sound is inversely proportional to the square of the root of the density of the gas. As you know, density of oxygen is 16 times the density of hydrogen. So we will consider over here velocity of the sound in hydrogen over velocity of sound in oxygen. That is directly proportional to density of oxygen will come to the numerator and density of hydrogen will come to the denominator. So root will take density of oxygen is 16 times of density of hydrogen. So 16 root will be 4. It means velocity of the sound in hydrogen will be equal to 4 times the velocity of sound in oxygen. Second is effect of temperature. Speed of sound in a gas increases with the increase in temperature of the gas. A reason is that with the increase in temperature, density of the gas decreases, and we know that velocity is inversely proportional to density and directly proportional to temperature. So with the increase in temperature, velocity of the sound will increase by 0.61 meter per second for each degree Celsius rise in temperature. So there is very important relation, that is Vt is equal to V0 plus 0.61 into T. Now Vt is the velocity of sound at T temperature, V0 is the velocity of sound at 0 degrees Celsius, and 0.61 into T, T is the temperature for which we are interested to find the velocity of sound. So here in this example we are interested to find the velocity of sound at 25 degree Celsius. So we'll consider this V naught 330, 0.61 into 25, and after adding we'll get 345.25 meter per second. This is the velocity of the sound at 25 degree Celsius. So rest of the part we'll discuss in next video. Thank you.